Hello everybody, and welcome to the final module video for Introduction to Logic. Um, in this video, we will be learning the main method, and the main method is our validity test for polyadic quantificational schemata. By the way, I apologize if my voice cuts out and it's kind of hard to hear. I'm still getting over this laryngitis, but I'm doing all right enough that I think I can get through this today. Okay. And so the first thing I'm going to do is I'm going to review the difference between free and bound variables, because this is the point in the course where you actually do need to know that to be able to apply the main method. Then the next thing I'm going to do is I'm going to give you the last two rules that we have that we need to use to employ the main method, and they will be rules for generating instances of quantificational schemata. I'll explain what that means when I get there. Then finally, I'm going to explain the method and go through some examples. And just a heads up, so for the final exam, I'm not going to be giving you punishingly difficult examples of this. I'm probably just going to give you one or two pretty simple ones. And just like with the method of existential conditionals, what I'll be looking for and what I'm going to tell the TAs to be looking for is not that you can do all of this without making a tiny little mistake, but that you generally know what you're doing, so that you set things up right and you proceed in a way that, you know, somebody who's studied and tried the examples and the exercises, as long as I can see that you've done that, that's really what we're looking for. You'll get at least most of the points. Okay. So I'm just going to go on to review free and bound variables really quickly. Okay. So if you remember, I've covered this before, but if we have, say, a schema like this, so in a schema like this, the variable x here is a free variable, and it's a free variable because we have these quantifiers that bind z and y. So z and y are bound variables. So a variable's free if it occurs without a quantifier to bind it, and a variable's bound if it occurs with a quantifier that binds it. Okay? So just another example to help you guys understand this. So if we have the schema of this, the w is a bound variable because we have this quantifier with a w next to it, and this u here is a free variable, right? So when we learn the main method, some of the rules that we can use are going to which variables are free and which ones are bound. So if that wasn't enough of a review, check out some of the previous videos where I introduced quantificational schemata. Okay, so I'm going to go through the steps of the main method, and then I'm going to pause when I get to the portion where you get the new rules. I think it's easier to just show you the method in order and then give you the rules when you need them. So the first step is just kind of setting it up properly. And there are two possibilities here. So we could either be testing a single schema for validity, or we could be testing an argument. And we're going to do two slightly different things depending on which one of those cases that we run into. So if we are testing a single schema, the simplest case for validity, the first thing we do is we convert that schema to prenex form. That's where all the quantifiers are out to the left, right? If you're not sure what that is, review the chapter on rules of passage. Okay, so that's the first thing we do. And I'm not going to give you ones that are very much work to convert into prenex form. The second thing we do is we negate it. When we negate our schema, And then we use our quantifier equivalencies to move the negation sign inward as much as we can. So I'm going to show you, so if we have the single schema, this, oops. And these are all from the book, and that's 100% on purpose here, in case you're following along. Okay, so if we have this schema right here, and we wanted to set it up according to this first step, single schema, well, it's already in prenex form. All the quantifiers are out there, so you don't need to do anything there. So what we do is we negate it, right? And then we use our rules to move the quantifier, or to move the negation sign to the right to the quantifiers. So if we use equivalencies in order, step at a time, we get, oops. Right. I picked the wrong example. It doesn't really matter though. And that was just using one of our quantifier equivalency rules. And then next we get this. So this is what it means to move the negation sign inward. And we stop here. We don't like try to do anything with that. We just want to get that. We just want to get the right of all of the quantifiers. So this is the first step for a single schema, right? We convert to prenex, we negate it, and then we move the negation sign to the right of the quantifiers or inward. Okay. So more commonly, you will run into an argument that you want to test whether or not the premises imply the conclusion, right? And so if we run into an argument, it's the same basic thing. So we convert the premises and the conclusion to prenex form. Then we negate only the conclusion. Then we move the negation sign inward or to the right of the quantifiers. And then after we've done for the conclusion only, if it won't happen that it's outside in the front on the other ones, because that can't convert to a prenex form with a negated quantifier out in the very front. And then we assume or add our negated conclusion with the negation sign driven inward to our premises. So again, this will be clear once you've seen an example. So let's assume we have this argument. Okay, first premise, second premise. Okay, then our conclusion is this. Okay. So the first thing we have to do is convert our premises and our conclusion to prenex form. And if you look at this first one here, that's the only one we have to do anything with. So the way that we would convert this to prenex form is we need to move this quantifier that binds the z. And because if we're taking it out of the antecedent of a conditional, it'll change to a universal quantifier. This becomes what I'm about to write. So, right, and then that's, everything's in prenex now. So the next thing we do is we negate our conclusion, and then we do the same thing we did with moving the quantifier to the right. And remember, so how that works is, so what I'm doing here, I'm moving the negation sign to the other side of this existential quantifier, and that'll change it to a universal quantifier. So the first step is okay. And that should make sense. So if I say to you, you know, there doesn't exist anything that's a pi, that means the same thing as everything that exists is not a pi. So I once again apologize that my voice is kind of crapping out here. Okay. And then next we just do that again. So right. And then this right here is our conclusion that's been prenexed and then negated, and then we've driven the quantifiers, or the negation sign, through the quantifiers. And so what we do is we add that as a third premise. Oh, oops. And this is just sort of how you set everything up for the main method. We're not actually doing anything new just yet. Okay. So, yeah, that's how you do the first step for both a single schema, if you're testing a single schema, or for an argument. That's how you set it up. And so next I'm going to explain step 2, which is where we generate instances, and that's where I need to explain some new rules. So do that second. Okay, so step 2 of the main method is really simple. We just apply these 2 rules that I'm about to give you, a universal instantiation and existential instantiation, to get rid of the quantifiers. And the goal of this is that we want to drop the quantifiers or instantiate our quantificational schemata in such a way as to give us a truth functionally inconsistent set of instances. I know this sounds really confusing, but once you see an example, I think it'll be clear. And the reason that we're doing that is, so just scroll up. So what we're doing here, when we took this, which was the conclusion, then negated it and added it to the premises, we're doing something that's known as a reductio, in other systems known as a reductio ad absurdum proof. And so what that means is that you take the conclusion of your argument and you assume the negation of it. And if you, on that assumption of the negated conclusion, end up with something that's inconsistent, then you know that the premises have to imply the conclusion. So don't worry about that just yet. Or don't worry about that too much. That's just how it might relate to another class, another logic class if you've taken one. And so I'm going to explain these instantiation rules momentarily, but there's kind of one universal restriction on instantiation. So this applies to both of the rules that I'm about to give you. And that restriction is when you drop a quantifier, so if you go from, everything's an F to like A is an F, right? You must replace all occurrences of the bound variable, of the variable the quantifier binds. Right. And the new variable must be free. in an instance. Yeah, so if you're dropping, I'll explain the rule in a moment, but we will use universal instantiation to go from something like this quantified expression with a bound variable to this free one, right? But you have to replace every occurrence of x in the schema with like an a here, right? And yeah, you can't, like this is wrong. Right, that's wrong. Don't do that, because there we didn't replace both of the x's. We just replaced one of them. Okay. So the first instantiation rule that we're going to learn is universal instantiation. Or UI for short. And so how this works is we drop the quantifier, and we replace the variable it binds with a new variable, or a new letter. I'm just going to write some letter. Right? And it doesn't actually have to be new, but it might help you if you always pick a new one. Right? So here is a schema. Right? And if we wanted to use UI, all of the schemata that I'm about to write are things that we could get through UI. So again, we just drop, and we have to work left to right. So we have to start out here on the left here with this x quantifier. So, right, so that's a legitimate use of universal instantiation. So is this one, right? We just replaced it with a B instead of an A. So is this one, right? We just replaced it with a Z. And you could actually do right. This one's legitimate too. It might get confusing if you don't pick new ones. And depending on how you did how you generated earlier instances, it might be the case that you have to pick like an X here. But if you can avoid it, it's probably better to pick new variables. You don't have to, right? And so with each of these instances, we could apply UI again. Right, so there we could have, FAB, right? We'll replace the Y with something else, right? We could also, because it's universal instantiation, we can do like FAA, right? I told you to pick new letters, but you don't have to, right? Because these are universal quantifiers. So what this says is that, let's read fxy as x is friends with y. What the sentence originally says is for every x and for every y, x is friends with y, right? And it follows from that if, if every object in our universe of discourse is friends with every other object in our universe of discourse, it follows from that every object's friends with it, or every entity in our universe of discourse is friends with itself, right? So we could also, apply it again here. We could get, right, we could apply it again here. We could get, right, we could apply it again here. we could get fx if we wanted to, right? Because we can drop the y here to any letter that we want. The only restriction is that we have to replace all of the occurrences of the variable that the quantifier binds. Yeah, universal instantiation's pretty easy. It's not the one that's going to trouble you. So the next instantiation rule and the last rule that we have to learn in the class is existential instantiation. Or EI for short. And so how this works is we drop the existential quantifier and replace all occurrences. Oops. Of the bound variable, of the variable the quantifier binds with some letter or with a new variable. I'm just going to write some letter. Okay, but there's a restriction, an additional restriction on this that's important. And the restriction is that I'll give you the easy way of understanding it. So the restriction is that all schemata that we generate with EI have to contain only new variables. And that means they have to be new, like, entirely, not just new in that schema or new kind of on that line. So if you have, let's say, I don't know, let's just pretend that we're doing our thing here. I don't want to set up a complete proof yet, right? So, and then that should be an A. And then we would cite this rule like 1 existential instantiation. Right, we cannot drop this Y to an A here because this A occurs, it's free on a previous line. So we could go like FA B, and that'd be fine because B is new, right? It doesn't occur anywhere previously in the proof. But we can't do this. And we can't do it because this A here it already exists in one line of our proof. And as a consequence, this is a mistake. So we have to observe this restriction on EI. And one of the reasons that I like Quine's system of logic is I can just tell you that it has to be new, and that's adequate. But so the technical way of saying this is that no instance generated via EI can contain a variable that is free in a previous line or in any previous line. Okay, so just gonna give you an example of some legitimate uses of VI here. So if we have the schema, right, this one, all of these are okay uses of existential instantiation. So right, and they're legitimate because well, we have the general restriction on instantiation where we have to replace all the occurrences of the letter, but there's only one, so I'm not going to screw that up here. And so we just have to be careful that we don't replace it with anything that's free on a previous line. And since we don't have any previous lines, right, all of these are going to be fine. Yeah. So I'm going to give you, just to hammer home how you can make mistakes with this, I'm going to give you some premises and instances. Oops. And then, so the way that we're going to do this is once we've gathered our premises and conclusion and done the pre-next it, negate it, drive the negation sign through thing, or if we just have a single schema once we've done that, what I like to do just for notation is I draw a line under that, and then when we generate our instances, I start lettering with Roman numerals. This is just to let me know where your instance or where your premises and conclusions stop and your instances start. I just find it's neat. But it's not paramount that you set it, make it look exactly like I do here. So if we then, applied UI to the first premise, giving us something like right, then we could not, what we can't do here is we can't drop this W using existential instantiation to any of the letters we've already had. So this would be wrong, what I'm about to write. Wrong. And it's wrong because this U here occurs free in a previous line. It actually occurs free in the premises, and those count, right? So if we wanted to do this correctly, we would have to drop this to a letter that doesn't appear free in any previous line. So we could do like... there, that should be fine, right? Because there's not this A right here doesn't occur free in any previous line. It's a new variable. Just to make this a little clearer, so this would be UI on 1, and then 2 here would be EI on 2, right? So those are the restrictions that we need to observe when we're looking at existential instantiation. So there are no restrictions on universal instantiation other than that we have to replace all of the variables. And so, if we wanted to go from line 2 here to something like UI 2. Right, so this is perfectly fine. This restriction only applies to existential instantiation. So if we want to drop an existential quantifier to a letter, we have to make sure that letter is new. But if we're doing universal instantiation, it doesn't matter if the letter is new. We can drop it to letters that are already free in previous lines. Okay? I need to rest my voice for a minute, and then I'll come back to this. Okay, so I'm just gonna do a few examples, and hopefully that'll make things a little more clear to you. I know it's a little confusing when I start explaining rules and you haven't seen me use them. So this is one of the examples that I used above. And so the first example, we're just gonna, if I ask you to test something like this, so a single schema for validity using the main method, here's what you do. So remember, the first thing we have to do is we negate it. It's already in prenex form. The first thing we would have to do normally is convert it to prenex form, right? Then we use our quantifier equivalencies to move the negation sign to the right of the quantifiers. So oh, I screwed that up, my bad. Still sick, can't think. Right, okay. So that's all we gotta do to set it up, basically. And then what we do is we assume this as our first and only premise. And we generate instances. And the goal again here is to find an instances without any quantifiers. We have to get rid of all the quantifiers. Maybe, actually, maybe we don't necessarily have to, but for most of these you will. And we want those instances to show up as inconsistent via truth value analysis. And I'll show you what that means. So here, this is pretty straightforward, right? We have these two quantifiers. We have to use each of our instantiation rules once. So the first thing that I'm going to do is I'm going to drop this universal quantifier, because you have to start from the left when you're dropping them, right? And because it's a universal, we can drop it to anything that we like. And if you look at the schema, if we want to get something that shows up truth functionally inconsistent, we need to find a way to make this whole thing and this whole thing end up with the same letters. You'll see what I mean, I think. And so I'm going to drop this y here to an x using universal instantiation, and that's fine because there's no requirement with UI, universal instantiation, that the variables be new. So right. And all I did there was, again, drop this universal quantifier and replaced all occurrences of the variable it binds, which is y, with another letter, x. Okay? And then here, the only thing that we're capable of doing is dropping this z to something. And it actually doesn't matter. So in order for this to work, we had to drop this y to an x specifically. But here, because of this free x in the antecedent. But here it doesn't really matter what we drop the z to. I'm just going to drop it to w, I guess. So we get not. Right. And so once we have gotten rid of all of our quantifiers, this is just sort of a truth functional schema. So if you want to save yourself some writing, so we have fxw here, fxw here. Okay, so that is the same logical form of not if p then p. Then we just do a truth value analysis on this. You could write this all in, but just make sure that you keep track, because if you assign like fxw to p, you cannot also assign like fxz to p. No, wrong. So you can replace these if it just saves you the time to write. these predicate compounds, I guess is what you call them, with a single propositional letter. However, make sure that you double check that you're actually they have to have the exact same appearance. You know, the variables have to be in the same order here, and each one that you're going to replace with p has to be exactly the same. And so, you know, not if p then p, so not, oh wait, and then, and so that's, both of these are going to go not true, false, not true, false. And so the way that this works is, but we wanted a set of truth, we wanted to get some truth functionally inconsistent schemata, or a truth functionally inconsistent schema in this case, I suppose, and we did. It's inconsistent because this always ends up in false, and because of that, we know that our original premise, the thing before we negated it, is valid. So that's how we do the main method with a simple example. That was pretty trivial, so I'm going to give you a more difficult one. Okay, and this is going to take me a second to write, so... And this is one of the other examples. This is the example that I used to set up an argument for step 1. Just let me look over that, double check I wrote it all right. Yeah, cool. I think I did. So remember, we have to convert our premises and our conclusion to prenex form. And again, I already did this, but just to hammer it home, the only thing that's not in prenex form is this one, because we have this quantifier here, but it's not all out in the front like we want. And so to convert this to prenex form, we use one of our rules of passage from last week's units. And remember, if we're taking something out of the antecedent position of a conditional or putting it in, it's going to change the type of the quantifier. Was that z? I can't remember. Yeah, okay. Okay. So that's prenext. Then the next thing we do is we negate our conclusion and just do that thing where we move the negation signs to the right. Okay, so we have our conclusion that has been negated with the negation sign moved to the right of the quantifiers, and so then we add that as to our premises. Okay, and then so these are all our premises, and then we're going to start generating instances. I guess I could, to make things a little easier, do it like this, where I start the instances with Roman numerals at 4. Okay, and so here's a strategy thing, and this is important because you can trap yourself in these in a way that you won't be able to finish unless you start over. If at all possible, what you want to do is you want to use existential instantiation first, right? And the reason for that is because there's this restriction on existential instantiation. So this, existential quantifier binding x here is that we can only drop that to something that's new, right? But with universal instantiation, we can drop it to whatever we want, and it doesn't have to be new. And so there's some times where you'll have to, if you if you used universal instantiation first, you'd never be able to finish the proof. You never get the sort of truth functionally inconsistent schemata that you want. So what we do here is I'm going to start with 1, like I just said was a good idea. And I'm going to drop that x to a w, I think. So right, okay. And then here, we can't do anything with an existential, right? So what we want to try to do is we want to try to find some way of dropping these where we can match up as many of the variables after the predicate as we can, so that we'll get something that's truth functionally inconsistent. So I'm just going to start doing my stuff. And this was, again, I will notice what rules you're using, but for the sake of the TAs, it might be a good idea to note where you're using existential instantiation and where you're using universal instantiation. So and here I'm just using universal instantiation on 3, right? And again, because it's a universal quantifier, it doesn't matter that this W is free in a previous line, right? So next, what I'm going to do is I'm going to drop this existential here. And again, it's not terribly important what I drop it to. It has to be new. But sometimes it will be important what you drop the quantifiers to, and sometimes it won't. That's just how this works. Right, and that's EI on 5. Okay. And then I got to do something with, my other premises, right? Yeah. So what I'm going to do next is I'm going to use universal instantiation on this, line 4. And here, what I want to try to do is I want to try to match up these variables here with something that I already have, so something like this, right? And so what I want to do here is I want to try and get this as much as I can in 4 to match up the letters of this in 6. At the very end, I will explain why I can't give you like the sort of precise instructions that you might be used to by this point for this. So what I'm going to do then is just this. Right. And this is just universal instantiation on 4, right? And then for the next step, what I have to do is I'm going to need to do something to 2, right? Because I haven't really touched it at all. And what I'm going to do is, since I have a universal quantifier, since I have a universal quantifier, I want to try to drop it to where this y here matches something else I already have. And I have the q here. I've been drop the existential quantifiers to a q for, the first predicate there. And so what I'm going to do on this line is just... right, and that was UI on 2, right, then next, and here we just need to get rid of the quantifiers in a way that will give us something that's truth functionally inconsistent. So we have, here we have this Q in the middle, right? Right. So what we have to do is we have to drop the two quantifiers in this and this in such a way that it'll, and again, there aren't like, there's not a set of rules here that will guide you precisely, but so we know that one of these is going to be this AQW is not going to change, right? Because those are all free variables, and this is not going to change. So for this and this, what we're going to want to do is we're going to want to drop these z's to the same thing, because that'll let us plug in truth functional letters and do a truth value analysis that'll come up inconsistent. So I'm going to work on, drop the existential one first here. So just AQS, and that is existential instantiation on line 8. And then for this one, I'm just going to drop this universal here to S as well. So that's okay. And so what we do here is, and as you do more of these, you'll get a sense of when you have something that might be truth functionally inconsistent. So what we do is then we make a conjunction with this line, and this line, right? And that gives us not, right? It's just a simple conjunction. Okay. And so we have two different, like we have AQS and AQW and its negation. So AQW I'm going to say is Q, and AQS I'm going to say is P. Right. And so this is what we have, and we do a truth value analysis on this. And I guess I'll start with Q, I guess. No, I'll start with P. And then so this one's easy. It's a conjunction with a false component, so it's false. Then here, we do our truth value analysis, so and obviously the conjunction of Q and not Q is always going to be false. So that's it. That's how you do the main method for a more complicated one like this. So to a certain extent, strategically, you should always drop the existentials first if you have the opportunity. But what you really want to try to do is you want to try to, and again, there's not an algorithm for this the way there is with the method of existential conditionals. So you got to try a few of these and get a general sense of how it works. But what you want to try to do is you want to try to match up when you drop the quantifiers using our instantiation rules. You want to get something where you kind of have as many of them as the same as you can, so that you can, something like this, right? Where if we replace it with P's and Q's, it'll come out truth functionally inconsistent. There isn't really a shortcut for me to tell you, what to do, other than always drop the existential quantifiers first, because of the way the restrictions on our instances work. So I think this is enough for you guys to try to do the homework assignments for this unit. And I will post some more complex examples, but the ones in the book for homework are not bad. I'm pretty sure they're not that bad. Oh, actually, I just gave you one. So try to do the one main method one in the book and see if you can get it right. I'll post, when I can talk a little more in a day or two, I'll post some more examples of this. But I guess now is the time to teach you a fun fact. And the fun fact about this is for polyadic quantificational schemata, there's no decision procedure for it. And we can prove as a consequence of one of Gödel's incompleteness theorems that there's no such thing as a decision procedure for this. So it's not that I'm being like lazy or punishing you by telling you that I can't kind of tell you what to do at every step here. It's that we know as kind of a matter of like logic, we're absolutely certain that there is nothing that we could, there is nothing I could give you that's just a set of finite steps that would lead you to the conclusion here. And yeah, this is where logic is both kind of useful because we can use this to prove very complex things about relations that obtain, but also very hard. There's no computer program out there that will assuredly terminate a validity test in a certain finite number of steps here. It just doesn't exist. It can't possibly exist as a consequence of the incompleteness theorem and the Church-Turing thesis. So yeah, go back and study what I did here and try the one in the book, and I think you'll do all right with it. But again, I'll be posting some more examples of this. Just give it a shot. The tricky thing is just really like figuring out how to match up the variables that you're dropping to correctly. And so hopefully that made some sense. Again, I will post some more examples of this where I go through them in detail and explain everything I'm doing. But I think that gives you enough to at least try the homework assignment in the book. And yeah, cool. Thanks for tuning in.